Okay, good morning everybody. Welcome to the next session on ADSP. So last time we looked at matched filters. Right? And remember, matched filters had the goal of minimizing the signal to noise ratio, basically to minimize the noise in the signal. And we had this little demo with speech. Right? So we had speech, we added noise, white noise, which was flat across the spectrum. And then the Wiener filter could actually reduce the noise. Although when listening to it, the difference was not so impressive as looking at the numbers that we saw here. So here you can see the mean squared error before and after Wiener filter. So this is the mean squared error before filtering, and this is the mean squared error to the original after filtering. So we compare the noisy signal with the original and then the output from the Wiener filter to the original. And we can see here that the resulting error power is less than half. So it was actually quite effective. We reduced the noise power by more than a factor of 2. So in that sense, it was successful. It basically did what it was supposed to do, except that it didn't sound so impressive. Yeah, so let's continue at this point and looking at this matrix A transpose A, which we use to compute the Wiener coefficients. Right? So what is actually this matrix A transpose A? Remember, A contains the samples of our signal. Right? In this case, contains the samples of our noisy signal. Basically, in this case, 10 samples of the signal in each row, shifted by one sample each. And when we then take A transpose and multiply by A, then we get basically a 10 by 10 matrix. Remember, the 10 came from the order of our Wiener filter. And then when we look at the content of this matrix, A transpose A, this 10 by 10 matrix, we see that each line looks like the one above, but just shifted by one sample, right, by one entry. So here we have this entry 1.08 times 10 to the 12, which appears in the second place in the second row, and so on. And here we have 9.1 times 10 to the 11, which appears then one place shifted in the next row, and it's actually also symmetrically on this side here. Right? So we also have the symmetry here from left to right. Yeah, although when we look closely, those numbers are not exactly the same. Right? When we look carefully. So this number and this number is not exactly the same when you look at the last digits here. So it comes very close, but it's not exactly the same. Also, when you look at those two numbers, right, here those first digits are identical, but when you look at the last digits, they're not exactly the same. Right? Mostly, but not exactly. Yeah, so for now we want to neglect those small differences. And we see that this is the 10 by 10 matrix, where the next row is almost like the previous line, shifted by one sample to the right. So it's an interesting observation. And in general, we can observe that this matrix A transpose A converges to the autocorrelation matrix Y of n if the length of the signal in the matrix goes to infinity. Right? So those slight differences that we observed in the matrix, they basically come from us taking a finite length signal. So in this case, we had just 200,000 samples. 200,000 is still a lot, but was sufficient to make those small differences that we saw in the last few digits. But if we assume that we have an infinitely long signal which never ends, then this corresponds to the definition of the autocorrelation matrix, which I wrote here. So A transpose A in the limit goes to the autocorrelation matrix, where this RYY is the autocorrelation of the signal Y. And to help your memory, this is the definition of the autocorrelation. So we have RYY of M. M is a shift between the signal and itself, and then we multiply the signal with a shifted version of itself, and sum over all samples. That's the autocorrelation. And here you can see the sum goes from minus infinity to infinity. So this fits to our definition of A transpose A if the signal goes from minus infinity to infinity. Right? In our case, A transpose A, we just sum over the length of the signal. So that's the main difference, and that's why in the limit this goes to the autocorrelation matrix if we have infinitely long signals. Yeah, since one row of this matrix is shifted by one sample to the one above, this is called a Toeplitz matrix. So this is a special kind of matrix, that's why it has a name, and it's called a Toeplitz matrix. And you can also read more about it in this Wikipedia link here. So when you then look at the expression A transpose X transpose, which in the Wiener formulation was in the right-hand side of our equation, right? We had A transpose A equals A transpose X transpose, or A transpose A times H, the coefficients equals A transpose times X transpose, then this expression here converges to the cross correlation. So again, if our signal is infinitely long, then A transpose A is identical to the cross correlation of the noisy signal to the clean signal. So here you can see the definition of Rxy. So M is the time lag or the shift. This is the noisy signal. This is the clean shifted signal. M samples. And if we then sum over all samples, we get the cross correlation. The cross correlation between the noisy and the clean signal. So this is convenient because it simplifies the formulation. And because then we can formulate our Wiener coefficients in terms of correlations, autocorrelation and cross correlation. Right. So in the receiver, we usually don't have the unnoisy, the clean signal, but we can estimate the above cross correlation function. So that's the advantage here. All we need is not the signal itself, but just the cross correlations and the autocorrelations. And that's often easier to estimate. So that means our expression for the Wiener filter here was the formulation for the finite length signal that we have in A, right? So here we have the pseudo-inverse, and this becomes, using the correlation formulation, the inverse of the autocorrelation matrix times the cross-correlation vector. Right. Same thing as before, except now we use the correlations. And this is an advantage if we have the correlations but not a test set. But on the other hand, this works if we assume we have infinitely long signals. If we only have finite length signals, then this original formulation actually gives the more precise answer. Yeah, and this matrix form is also called the Yule-Walker equation, right? This form here. And the general statistical formulation using the correlations is called Wiener Hopf equation. And so you see those two names, and in our context, it's basically the same thing. Right? We have the Yule-Walker equation using the matrix, and the Wiener Hopf equation using the statistical formulation. Yeah, you can also read more about it in this book by Monty Hayes, Statistical Signal Processing Modeling. He's a professor at Georgia Tech, where I used to be as a student. And I found this book is quite in-depth and easy to read. So So I can recommend it if you can get it. Yeah, so this general statistical formulation has now the advantage that we can design Wiener filters by just knowing the statistics, the autocorrelation function of our noisy signal and the cross-correlation function of our noisy and original signal. And we don't need the signals itself. So observe that this autocorrelation and cross-correlation can also be obtained from the power spectra, or the cross-power spectra, the product of two spectra, of the respective signals. So sometimes this is also an advantage if we just know or estimate the spectrum, but don't know the signal itself. Right? When you look at speech signals, often they have typical spectra. Yeah, so this power spectrum of the noisy signal can usually be measured since it is the signal to filter, and the spectrum of the original signal X usually has to be estimated using assumptions about it. For clean speech, for instance. We just look at the typical spectrum for clean speech and say, this is it. Or we assume noise is everything below a certain threshold, and then clean speech is everything above. Yeah, so for instance, we know typical speech spectra. If you want to adapt a Wiener filter in a receiver, we take this typical speech spectrum and measure the noise level at the receiver. So remember, this was an important ingredient of our Wiener filter. We need to know how much noise we add. So we measure or estimate the noise level at the receiver, and then we can add the power spectrum of the noise to the power spectrum of the speech to obtain the power spectrum of the noisy speech. So in our case, it was flat across spectrum. Yeah, and this is the power cross spectrum of the clean speech and noise, or the Fourier transform of the cross correlation, because we assume the speech and the noise are uncorrelated. Yeah, to use Wiener Hopf, we simply apply the inverse Fourier transforms to the power spectrum, and then we get the correlations. Yeah, so that is sufficient to compute the Wiener coefficients using above formulations. So all we need to know is the spectra, the clean and the noisy spectra. Yeah, makes sense so far? So now you also have Python examples for the Wiener filter, and I found that often helps a lot figuring out how things work. Right? If there's something that's not clear, easily you can try to figure it out looking at the code. Okay, so let's go to the next set of slides, number 13. Filters. So mesh filters were the other type of filters which deal with noise, just that this is about minimizing the influence of the noise. It's not necessarily about high fidelity. So the goal of the meshed filter was that the output of the meshed filter with a noisy signal comes close to the output of the filter with a clean signal. So the influence of the noise at the output of this meshed filter should be minimized. Right? But the output of this meshed filter should not necessarily be close to the clean signal. So remember, unlike the Wiener filter, where we had the goal that this is the clean signal, here we also have the Wiener filter itself in it. Right? So we have the Wiener filter on both sides. The matched filter, CHM, the matched filter is on both sides. The Wiener filter was only on this side. Right? Where ND is some signal delay. So we leave this matched filter some delay for best performance. Yeah, so here we don't want to have signal fidelity. We just want to have high signal to noise ratio for detection, where this noisy signal, as before, is just the sum of our signal to be detected plus some noise, additive white noise. So this V is some noise here. So application examples are communications where you would like to detect a 0 or 1, for instance in CDMA, where each user gets a unique pseudo-random 1-0 sequence, a so-called chip sequence, to represent a 0 or 1, in which different users and signals are separated using matched filters. Right? So this also shows that the signal to detect here is null. Right? It's a fixed signal. It's not a statistical signal as in Wiener filters. In Wiener filters, we just need to know the correlations or the statistical properties. Here, we really have a known signal that we want to detect. Right? Yeah. So another example is for detecting known signals or patterns like objects or face recognition in images. In general, we would like to detect deterministic signals X of n. Right? So we know what we're looking for, we just don't know where it is. Right? We have to detect it. So this means our goal is to minimize the signal to noise ratio at the moment of detection with our original signal X of n and the noise V of n. So this is this formulation for the signal to noise ratio. Here we have the clean signal after matched filtering. Right? And this is the power magnitude square. It's basically our power here, the power of the signal. And this is the noise. So here we have the expectation, which means average in our case, of the noise filtered by our matched filter. Magnitude square again taking the power of it. Right? So signal divided by noise power. Signal power divided by noise power is our signal to noise ratio. Yeah, we would like to maximize this signal to noise ratio at the time of detection using our filter HM, the matched filter. So basically all we need to find is an HM which maximizes this expression. To do that, first we assume V of n to be independent white noise. Again, that simplifies our derivation. Then the denominator of the signal to noise ratio expression is just the scaled fixed power expression. Right. So here you have the noise and you filter it, and all that we are able to change is the coefficients of our matched filter. And yeah, using our formulation of matrix V for the noise signal and the row vector H of m or HM for our filter, we can obtain this expression here. So here we have our noise again, filtered by our matched filter. And then we rewrite this convolution again in terms of our matrix multiplication, as we did with the Wiener filter. Right? So here we have V as this matrix capital V, boldface capital V, which contains the coefficients of the noise signal in each row. And then here H transpose M is the coefficients of our matched filter as a column vector. Right? So we have matrix, torn matrix, times our small column vector here, and that gives a vector as the output of our matched filter. Right? So this is basically the noisy output of our matched filter as power. Make sense? Yeah, and then we can rewrite this expression here, this magnitude square, just as basically the square, take the expression and write it again with its, multiply it with itself, which I did here. So here I took the transpose expression times the original expression. So that's the same. So then here in the middle, you have V transpose V, and this looks very similar to this A transpose A that we had in the Wiener filter. So V was this Tor matrix, V transpose is this fat matrix, and the output is this small square matrix. Right? So again, this might be 10 by 10 if we have 10 coefficients. So then we have this autocorrelation matrix here. This again is our autocorrelation matrix, multiplied from both sides with our coefficients from our matched filter. Right. And since we have the expectation in here, the only statistical part is in V, the noisy samples here. This is deterministic, H is fixed. This is what we want to have, what we want to find. So we can draw in the expectation to this part. This is what I did here. So here we have now our autocorrelation matrix. Yeah, and this autocorrelation matrix for noise, how does a noisy, or how does an autocorrelation matrix of noise look like? What's the autocorrelation of noise? If you have no shift, it's the power of the noise. Right? But if you shift it by one sample or more, then there's nothing left, right? Because there's no correlation if we have white noise. White noise is basically random samples with no memory. And if one sample is independent of the next, and you multiply those and take the average, then it can be positive as well as negative, and an average is 0. Right? So any shift 1, 2, or 3 or larger will be 0. And that means when we look at the autocorrelation matrix, identical shifts, the shift 0 is on the diagonal. Right? Again, it's a Toeplitz matrix. First row we had shift 0, shift 1, and so on. And then in the row below we have shift 1, shift 0, shift 1, 2, and so on. So on the diagonals we have the power, and off the diagonals we have zeros. So basically, if this is white noise, now this white noise assumption becomes important, because only for white noise, this is the identity matrix times the noise power. Right? If we have non-white noise, then this simplification would not apply. Remember, non-white noise means the noise goes through the filter, and the filter then introduces memory into the signal. And that means this assumption of identity is no longer true. But if we have white noise, then indeed this becomes an identity matrix times the power of the noise. Right? So here it shows where this assumption really helps. Even though this white noise assumption might not be true in general, right? But it helps us finding a solution. Yeah, and this is already quite simple. So this is just a number, the noise power, and basically what we are left with is the coefficient vector hm times its transpose. So vector times vector transpose, and this is basically the power of the coefficients, which is in the coefficients. Easy enough. Yeah, so this is what I just said. Autocorrelation function of noise, is a weighted delta function, so white noise. It's true for white noise. Since noise samples are uncorrelated for all their neighboring samples, they are only correlated with themselves, and the correlation with itself is simply the noise power, sigma squared. Yeah, so the autocorrelation matrix hence has all 0 entries except on the diagonal, where is the noise power, hence the noise power times the identity matrix I. Yeah, so the last expression is simply the squared norm, the sum of the squares of the coefficients of our vector, of our filter coefficients. Multiplied within this one. So now we can simply decide to keep the above norm of our filter vector constant, right? Because that only affects the volume that comes out, basically, or the straight out. It's basically a factor on the output. And the factor doesn't really matter, we can always change it. So we can just decide to keep it constant. And that means the denominator then is constant. If you have constant noise and you have this constant coefficient power, then the entire denominator is fixed. Right. So that means we only need to maximize the numerator of the SNR fraction. That means the entire denominator is fixed, and we only need to maximize the numerator in order to maximize the signal to noise ratio. Right, and the numerator was this x filtered by the matched filter and taking the power of it. So basically we want to maximize the output of our matched filter for our desired signal, given that the power of the coefficients is constant. Right. So here we can also rewrite this equation again in terms of vector multiplication. So here this x is our signal as a vector, and here this is our matched filter. And this works nicely if the signal here has the same size as the number of coefficients in our matched filter. And this is an assumption that we can actually make because x, our desired signal, like in the chip sequence, is often much more compact than, say, a speech signal, which may go on forever. Right? This is also a big difference between matched filters and the Wiener filter. Wiener filter, basically we assume infinite signal length. Here in the matched filter, the signal to detect is usually small. It's some chip sequence for communications or a phase which has a certain number of pixels. So it's usually not so big. So that's why we can actually choose the matched filter to be the same size as the signal to detect. Right, and this is what I did here. Yeah, so analog to our matrix formulation as a scalar vector multiplication with HM as our row vector of the matched filter impulse response. And now with only one row of the signal matrix A from the last time, for only one convolution at a time. Yeah. So maybe I should add this. Observe that for matched filters, the signal to detect can be much shorter than for the Wiener filter, and hence we can decide to make the matched filter as long as our signal to detect. So this is a convenience. You can just choose the same size. so this is now our signal as a row vector. And we flip it because that fits to the convolution. Right? So we start with the last sample and then we go down. So L is the size of our filter vector, and observe that that it is time reversed to obtain a value of the correlation function of the convolution. So how would you do it? When you have vector multiplication, you have two vectors here, vector x and a vector h. X is given, h is what you're looking for. How would you choose h in this context to maximize the result? So remember, this is simply a vector multiplication, a scalar multiplication. So you have one vector given and one you're searching for. So imagine this vector h is perpendicular to this vector x. What's the output? 0, right? So that's not a good solution. So which maximizes the output?
And they are in the same direction.
Exactly. So if they're parallel, right, then we maximize the output. So basically, this is the solution. Right. So when is this parallel to x? How do we have to choose h? Yes.
Sir, can you explain why, like for matched filters, we can use much shorter signal to be detected can be much shorter than Wiener filter?
Yeah. For instance, if you want to detect a phase, right? The phase is much shorter than, say, a real that you want to denoise. So it was a typo, right? Therefore, matched. Or you want to detect a certain binary sequence, right? A chip, which is maybe, I don't know, a dozen or so. But speech, for instance, usually goes on forever and you don't know how long it lasts. Right? So that's different. For Wiener filter, you just have a statistical description of the signal you want to detect. For matched filter, you know exactly what you want to detect.
Okay.
Right? It's a known signal of a known length. And this is what you want to detect. And that's why you can decide to make h same size. And that leads to this convenient formulation here, where we can actually see the solution by looking at it.
This means like for Wiener filter, we'll usually have filter length to be much longer. Is that the understanding?
No, not necessarily. You have to choose a filter length for the Wiener filter such that you get a good solution, good noise suppression, and that depends on how complex your signal to filter is. So for instance, if you have speech, then it turns out often like 10 or 12 coefficients are good to model the spectrum of the speech. Right? Remember from last time, we want to suppress the spectral areas where we have a bad SNR and keep the area where we have a good SNR. So that means we need to model the spectral shape of the speech. So the speech goes up and down, so we just need to have enough coefficients to model this up and down of the speech. Right? So it depends on the signal that you want to denoise, how many coefficients you need.
So for in your formula, H transpose is RYY inverse into RXY for Wiener filter.
Yeah.
The size, the number of correlation coefficients you take depends on the problem we are working on.
Yes, right.
It can vary from problem to problem.
Exactly. Right. Yeah, good point. Yeah. And it's often a try and error. You just try out, and if it's not good enough, you just try to add more coefficients.
But for matched filter, we know what we are detecting, so the filter length is exactly the same.
Yes.
We need not trial the size.
Well, you could make it longer, for instance, but it wouldn't really help. Yeah, so here it's more given by the signal itself. Indeed. Right? Because here exactly you know what you're looking for. Right. So, yeah, what coefficients now do we need to choose? So we know x and h. H basically needs to be parallel to x. How do we get it?
take kind of we kind of an average of the input signal or something?
Projection of H and X.
Well, when we multiply the two, that's basically the projection. But we found that we choose H such that it's parallel to X, that we get a maximum output. Right? But so how do we get how do you get H parallel to X?
When they are squared by scalar.
Again?
H is like a scalar times X.
Yes, exactly. So basically, H is X times some arbitrary factor. Right? And that's basically the solution. So H just needs to be identical to X. And this X turns out to be the time reversed signal. Right? We take the signal, time reverse it, and that's our coefficients for the filter. Right? And I have a little bit more exact mathematical proof here. So here we see the X, right? The X is the time reversed version of our signal to detect. So that means our filter also needs to be the time reversed version. Yeah, and to see this solution that we were able to see by looking at the problem, we can apply the Cauchy-Schwarz inequality. Have you all heard about the Cauchy-Schwarz inequality? Very good. So you can actually read about it here in this English Wikipedia article, quite nicely described. And this is exactly about this problem. We have A times B, right, or A transpose times B, two vectors which we multiply, and we want to maximize it, and we see that the maximum is basically the magnitude of A times the magnitude of B. Right? This is the maximum we can get. And this can also be written using the norm notation. So we have this norm of A, this is the magnitude, and A comma B is this multiplication. So this is actually the more general formulation of the Cauchy-Schwarz inequality. So here you have magnitude A comma B as our product, scalar product. We know it's less or equal to A norm times B norm. And we want to reach the magnitude, the maximum, and actually Cauchy-Schwarz tells us when this is the case. And this is exactly the case if both vectors are collinear, or B equals K times A. Right? So this is what we just saw, with some scalar K. So this shows us how to minimize our task, how to solve the maximization task. So if A is equal X, and B is equals H of M, then we have this task here, and that shows us that H needs to be just some factor K times our vector X. It basically comes out of Cauchy-Schwarz. And we can also choose the factors K equals 1 for convenience. But we don't have to. So keep in mind, if we choose K equals 1, then doesn't necessarily mean that we fulfill this norm to be some value. But it doesn't really matter because we just want to maximize the output. So we can choose this K whatever we want. Yeah, so since we have this inequality for all time steps of our convolution, we choose N where the row vector X has the maximum energy. So this is where we capture the entire non-zero waveform of our signal X with our filter. So this is just what I mentioned before. Right? We basically have choose X, H to be as long as X. Since our filter vector H contains the time reversed impulse response, we obtain the entire time reversed signal as our matched filter. So here, this is the result now. Yeah, so assuming our signal to detect is located between 0 and L, so that we have the same length, basically. We can always make it longer, but that's kind of wasteful, because then we have zeros at the end. So since we have a convolution of the signal with this time-reversed version, we get a convolution of length 2n minus 1 samples with its maximum at the center when both waveforms completely overlap after L samples, which is exactly the signal length. Right? So basically at the end of our signal we get a detection. That's the maximum. Hence we get the detection of our signal after we completely received it at the end of our signal. And after that basically it tapers off. Yeah, observe, since we convolve the signal with a time-reversed version of our pattern to be detected, this becomes identical to computing the correlation of the signal with the pattern to be detected. Right. Convolving with a time-reversed version is the same as correlation with itself. So you can also see a matched filter as a correlator. You have a filter, and this filter can be seen as a correlating pattern, and you just take your image or signal to be received and correlate it with your filter column. And this is also interesting because, for instance, on Pytorch for deep learning, when you say convolve, it actually does the correlation. So sometimes instead of convolution, indeed correlation is done. So that's why you have to be careful and read what it actually is doing. Right? When it says convolutive layer, it's actually doing a correlation and not a convolution. But you can find this in the description. So this might easily lead to confusion or to bugs if you don't read this description carefully. Yeah.
So like it can become like a template matching kind of thing?
Yeah, basically it's kind of template matching,
So
sort of. Yeah. Not exactly, but it's along those lines. Yeah, also observe the longer the signal is, the more energy is captured in it, and the higher the signal to noise ratio will be at the time of detection. This is important, for instance, for very, very weak signals, like in deep space communications. Right? So in deep space, you have only very weak signal, extremely weak. Right? And basically the output of your mesh filter is the power in your signal that you want to detect. And the longer you make the signal, the more, I should say, the energy. If you have weak power and you have longer time, you get more energy. Right? So the energy grows the more time you have to transmit a symbol. The noise also grows, but not as much, right? Because the noise partially cancels out. So that means you get a better signal to noise ratio if you have longer sequences. So in deep space you want to make your bits much longer than, say, on Earth to get a good detection. Yeah, that's why you get a much lower data rate. When you have weak signals, the data rate goes down. Yeah, there are also versions for continuous time. Here I have an example for continuous time, but we don't really consider it here in our context because everything nowadays is digital. So in conclusion, the matched filter has the shape of the time reverse signal to be searched for. Simple enough, basically. And now I have a Python example for a matched filter. First we need a signal to be detected. And we just take a length 11 signal. So here construct a signal to be detected. So here we define our sig. And in our case, it's simply a sequence of numbers between 0 and 1.1 in steps of 0.1. So an increasing ramp function. So it increases and then it goes back to 0 all the time. Right, so this is the output, goes from 0 to 1 in steps of 0.1. And then we can plot it. This is the output. Right. It's simply goes from 0 to 10, goes up, and then goes back to 0. Just an example. Can be anything. Now we can add noise and extend this length of our signal. So now we assume that our signal to be detected is hidden in a longer sequence with noise. It appears somewhere in this longer sequence. So I'm constructing 20 noise samples, right, equally distributed around 0, because here I'm subtracting 0.5. And now I'm appending zeros, the signal, and zeros, and add it to it. So here, this is our signal to be detected, and I add zeros in the beginning and zeros in the end. So altogether we get 20 samples again, so that we have the same size. So we have noise plus our signal shifted. Make sense? So now we can plot it, and this is how it looks like. So, can you see the ramp? Well, it's now actually harder to see, right? So it starts here sample 5 and goes up to 5 to 15, so right here, and then it goes down. So the rest is just noise. So here basically is the ramp. So it's actually kind of hard to see, right? When you just look at it with your eye, it's almost dominated by noise. So now we apply the matched filter. So the matched filter is simply the time reversed signal. So here we go from 0 to the end, basically we take negative steps, we go from the end to the beginning. So this is by basically flip it out. So the time reverse signal. Yeah, and then we take the signal in noise and filter it with our matched filter. Okay, so this, remember, this is the forward path, the FIR part. The IIR part is not used, that's why we have a 1 here. So then this is just an FIR filter which contains the coefficients from the reversed signal. So this is our matched filter. So then we can take a look at the output of this matched filter. And we can see this is the output. So, what do you think? Well, it's less noisy, right? But can we see the ramp? Sort of. Do we expect to see the ramp? Well, not necessarily, because after matched filtering, remember, our goal was not fidelity, was not signal fidelity. So we don't really expect to see the signal. All we need to see is the maximum peak at some point where the signal is supposed to be. And you can see the maximum is here, number 14. Right? So our matched filter tells us that it thinks our signal to detect ends at sample number 14. Right? So, let's see. Yeah, so this is now the output of our matched filter, and we can see that we have a maximum at time 14. So maybe we can actually see it when we plot the clean signal here from the code. So I can just try it here with my terminal shell. Back. So IPython minus PyLab, and then just copy the signal here. The signal is a range. Copy. Paste. So here we have the sig. Values from 0 to 1, and now embedding in noise. Excuse me. bit too easy for our match filter, right? Because in reality, we don't know where it is. So this is now our shifted version. Save shift. And now we can say plot, save shift. And this is what we get. So remember, this might be, for instance, our chip sequence for zeros and ones, or maybe a face that we want to detect. So we don't know where it is. Somewhere, right? So here, basically, I'm shifting our signal to detect at some point. Right? We basically assume that we don't know where it is. And here we can see, here at 15, it's back at 0. So the last sample was indeed sample number 14. Right? So that means our match filter detected it correctly. Yeah.
Like there might have, it's a possibility that a signal might have multiple peak points. So,
Yeah, but that's bad.
Yeah, but like I'm sending 2 or 3 bits and it has like step kind of a step.
Yeah, if you have multiple signals, then at each signal you should have a peak.
So in that case, that match filter should be made in the sense of that what we are supposed to detect.
Yeah, right. So each time the signal is present, we want to have such a peak here. Right? So this peak should appear every time it sees this signal to detect.
But in this case, it's a global peak.
Right, because you only have one of this pattern, right? We could also have multiple patterns. So for instance, if we just append the same sequence again, then the output of this match filter would appear again. So each time you have the signal, you would get this peak. Well, maybe that might be an interesting example.
Excuse me, is this filter reliable for speech signals?
Yeah, because speech is not a deterministic signal. It's different every time somebody speaks. Right? So you cannot use a matched filter to detect speech. I mean, you could, but it's maybe not working so well. Because when you look at the waveform, it sounds the same to you, but the waveform will be different each time. And here, this is really a waveform detector. Maybe it works better if you look at the magnitude spectrogram of speech. Right? If you want to detect certain vowels in speech, for instance, in the magnitude spectrogram, they look more similar to each other. So in that case, if you then take a two-dimensional matched filter, right, where your spectrogram, remember, is frequency and time, so you have a two-dimensional signal, and then you could apply a two-dimensional matched filter. But then, of course, you also would have to use two-dimensional convolution. Do you know two-dimensional convolution? It's basically the same as one dimension, it's just along 2 dimensions. Right? Basically, in 1 dimension you shift along 1 dimension, in 2 dimension you also have the other dimension to shift over. So the output is also 2-dimensional.
I mean, that is for the images, right?
Huh?
For 2D convolution for the images.
Yes, exactly. Yeah. So, for instance, low-pass filtering for images, you would do 2-dimensional convolution. Basically, you would treat this magnitude spectrogram from speech as images. And you would then detect certain pattern in that image. Yeah, but that shows the basic property. This expects a deterministic wave, right? A known wave, or a known pattern in an image, like a face. Right? You would, if you know a certain face, it needs to be the right size and the right orientation, right? And really the same shape. And then you can apply a matched filter on images to detect a certain shape. Basically, you would take this image and correlate you would take the face as image and correlate it with the image where the face appears. Yeah, so after detection, you see indeed here number 14 is the peak. But also observe the peak is not very narrow, right? It's kind of a wide peak. So the position to be detected might not be so precise, right? But this is also something that we didn't specify. We just wanted to say we wanted to have the maximum output, but we didn't say we want to have the peak as narrow as possible. Right? So it's doing a good job. It's giving us a good high output, but then the neighboring values might also be somewhat high. And you could imagine when you have a little bit more noise, then this becomes more difficult and blurry. So this is actually one of the disadvantages of the matched fit. You might have a wide maximum. It's a little bit easy to precisely say where exactly is the pattern. Yeah, so match filtering did actually a good job here, right? So the match filtering process can also be viewed as computing correlation of the noisy signal with the original signal, as I mentioned. Yeah, now we are getting to the convolutional neural network implementation. This is actually along those lines which I just mentioned. We didn't specify the width of the peak. With convolutional neural networks, we actually can do it. Right? With convolutional neural networks, we can specify a target, a desired signal, and this target should be also narrow. So it should be a high peak, and the peak should also be narrow. Do you all know what convolutional neural networks do?
Basically, we are trying to get some particular features which we are trying to do. So
Yeah. It's basically, in the simplest form, this is basically a trained filter, right? So we have a signal, we give it a signal which is called the training set. Then we also give it a desired output, for instance, the peak at the instance of detection. And then let the training figure out the best coefficients for this desired output. So basically, given input, given output, it figures out the coefficients which best fit. And that's basically all. And then it uses numerical optimization to find the best coefficients. So in our case, we used a closed form solution. We derived it with Cauchy-Schwarz, right? In the case of neural networks, it uses numerical optimization. Did you all have numerical optimization? It's very interesting. You should learn it. Yeah, so do you know what numerical optimization is doing? So basically, it adapts the coefficients piece by piece such that it's more and more reaching the target output. Right? So it gives you an input, then you start with some random coefficients, they give you some output which is not very similar to the target that you want to have. And optimization updates the coefficients piece by piece such that the output becomes closer and closer to the desired target. That's numerical optimization. Basically, it gives you a solution to a problem where you don't find a closed form solution. You let the computer do the work, basically. Yeah, so, right, this is what I just mentioned. We got a high peak for detection, but the peak was somewhat broad, which makes determining the precise location of the signal more difficult. This is because we specified as a target for optimization that we want to have a high peak, but not necessarily a narrow peak. To remedy this, we can use numerical optimization instead of our closed form solution for match filters. So here's the numerical optimization. Very powerful. And it turns out in recent years, numerical optimization became more and more important. And it actually made deep neural networks possible. Right? Only advances in numerical optimization made those deep neural networks possible. And of course, powerful, fast computers. Right? So everybody should know numerical optimization because it became so important. Yeah. For that, we can use the optimization of a neural network library like Python's Pytorch. Do you all know Pytorch? Who knows Pytorch? Who doesn't know Pytorch? Oh, let's see. Okay. Do you know Keras? Who doesn't know Keras? Okay, maybe the same. Yeah, see, those are two libraries in Python for neural networks. And if you want to implement neural networks, they make it convenient. Yeah, and I found that Pytorch is convenient because the print command works everywhere, and I found that important and useful for debugging, and that's why I like it. So the following example also serves as a short introduction into neural networks and its terminology. Do you all know neural networks? Who has not heard about neural networks? Everybody? Okay, great. So maybe you heard that neural networks become also more and more important. For instance, those home assistants which can recognize speech are based on neural networks, deep neural networks. So we can implement our filter using a one-dimensional convolutional layer with the function conv1d, without bias and without a nonlinear activation function. So this then also serves as a quick introduction into neural networks. So here, this is the function. Rather, it's an object. So the library Pytorch is actually open source, and you can download it for free from pytorch.org. So as usual for Python, everything is open source. Almost everything. So for it, we need to specify a training signal, and here our signal to detect the ramp function x and the target signal y, which is the desired output of the convolutional layer, which the optimization should reach as closely as possible during the optimization, which is called training for neural networks. So neural networks use their own terms, and instead of optimization, they call it training. Right? And here is now the training signal. Right? X is our signal. You can see this is the shifted signal. In the beginning and the end, we have our zeros. Right? And Y is the desired output. So we have the training signal. Our training set. So here we can see this is this desired place where it should detect. So here just choose Y of 16. So it's actually a little bit later than our previous example. But it doesn't really matter. So observe that for the target, Y is specified a single peak, the 1, at the position the filter should detect the signal, and zeros everywhere else. So this is now the prescription for a very narrow peak. Right? 1 at the point of detection and 0 everywhere else. Also observe that this is exactly 1 and not some large value. Right? It's exactly 1. Yeah, so this leads to a minimization of the output outside the signal detection, which we didn't have in our closed form solution. Right? So this becomes then less confusing for us. We specify our convolution detector layer as detector here sequential. Sequential means we have a sequential neural network. This is just the object. and this object contains this convolutional 1D layer. Right. And here you have the arguments in channels, just one, because we have a one-dimensional signal. Out channels, one, the output is also one-dimensional. Kernel size, kernel is now our filter. Right? And kernel size means the size of our coefficients. So here we take 11 coefficients in this case. Stride means downsampling after filtering, which we don't do here. So again, a different term. We call it downsampling. In convolutional neural networks, it's called stride. Same thing. Padding. Here padding means the way the convolution is computed. So this means it adds 10 zeros at the end and at the beginning to get more output samples. Right? It zero pads the signal. And bias is false. Bias means the addition of a fixed value. We don't want to add something fixed here. Right? That's why we set it false. Yeah, and observe that here padding equals kernel size minus 1, which leads to a causal filter, meaning all its inputs are not in the future. Right? It means it actually starts when the signal starts. It starts with sample number 1, and that means that filter length minus 1 samples need to see zeros before the signal begin. Right? And that's why we need to choose padding equals kernel size minus 1. Yeah, so this implements our linear filter as detector. The optimization we apply minimizes the mean squared error, the so-called L2 loss function. So another term that neural networks use, they call loss function what we would call error function. Yeah, now we can let the optimization or training run on the same RAM function as before and display the output of the detector with a clean and noisy signal as input. And we let it run here with Python 3 from our terminal shell. Our Linux terminal shell. So we use Python 3 because Pytorch only works with Python 3. Pytorch, this is my program that I wrote, and maybe I should show you. So here's this little program to do it. Quit in here. So let's see what's here. Yes, gedit. Can you all see it? So here's my little program, and you can see here it imports Torch, and Torch engine, it's a sublibrary. It uses NumPy, Matplot, WebPyplot, and sys for the argument. And you can see it uses Pickle for the coefficients. Yeah, so here we need this function signal to Pytorch because Pytorch uses different signal or number types. Right. So Python Pytorch uses always Pytorch tensors. So basically it is always based on tensors. Tensors are multidimensional arrays. Right. So it uses Pytorch tensors. So here you can see I'm taking the input x, which is our signal for instance. It adds dimensions because it also wants to have another channel dimension and a batch dimension. That's how neural networks are organized. They usually have several batches for training, and they have several channels, not just one. So we need to have those dimensions because they expect it. Then I convert it to torch tensor. So this is now a Python array, and here it will a NumPy array, and it's turned from NumPy to a torch tensor at this point here. Yeah, and here I'm setting it also as type tensor. So it's just a conversion, different type and added dimensions. And since I need to do it multiple times, I defined the function for it. And this is now the actual neural network. You can see class confnet. So I'm defining this class here, which is an object which I can use. Here I'm using the init function to basically set up the convolutional network with the default values, which you can see here. So here, detector, sequential neural network. Here's my 1D convolutional network. Here's the number of input channels, the number of output channels, the kernel size, the slide 1, padding 10, and no bias. Right? So basically this defines my neural network. And this function forward defines how I compute the output. It's very simple. I'm taking my detector here from the step above, give it the input x, and then return the output. So that's basically trivial. But I need to define it. So then I have the main part where I actually do the computation. So x is now our RAM function hidden in the zeros in the beginning and the end. So here you can see the RAM. Yeah, printing it. Here I turn it into a torch tensor. Then here this is our target, the desired target at the output. I'm setting it, presetting it with zeros, and then step number 16 I set it with a 1. So this is desired output. Then again I turn it into a torch tensor. Here I'm showing the input and the target. And here I'm defining the model from the class above. Remember, I defined the class confnet, and that's my model now. So the model is now the object which contains my neural network. Here I'm defining the loss function. There's also an object here now. Mean squared error loss, size average equals false. Here basically accumulates. It doesn't really matter in our case. So this is the loss function. We have many different loss functions to choose from in Pytorch. So mean squared error is just what we choose to use here because that's the same as our closed form solution. But we can also use other loss functions, and that might be actually interesting for detection problems. Right? Mean squared error, remember, we choose just because we get an easy solution with Cauchy-Schwarz, but it doesn't need to be the best. And here with numerical optimization, we actually have the choice. Right? We have many more possible loss functions that we can choose, and maybe some of those are better than the mean squared error. So that's also something we can try. Then here we set up the object for the optimization, and I'm choosing ADAM. ADAM is for adaptive moments. It's basically statistical gradient descent with artificial moments to actually come across local minima. Do you all know gradient descent? Who has not heard about gradient descent? You all heard about it? Sort of. Gradient descent, gradient is basically the derivative, multidimensional derivative. It shows you the steepest way down. Right? And this is the simplest numerical optimization. You update the coefficients such that you follow the steepest way down. Right? And that's why this is also called steepest descent. So basically, this is what this is doing, this ADAM is doing, except that it also introduces some inertia to overcome local minima. So it can go down and up and then go down. And this is actually a quite common optimizer for neural network. It turns out to be more powerful than statistical gradient descent. Yeah, and this loop is doing the numerical optimization. So it starts with some random initial point x, computes the output, and computes the loss, meaning the error between the obtained output and the desired output. So here, this is obtained, and this is desired. So we compute the loss between the two, and we want to minimize this loss. And this is done in this for loop 5,000 times. So we start with this initial point. Here I'm displaying the current loss. Here I'm using zero grad, which means I zero out previous obtained gradients. Here's the loss backward. So basically here we compute the gradients from the output to the input for all the coefficients. So this is basically the chain rule of gradient descent. If you compute the gradient or the derivative of a function, you have to apply the chain rule. Outer derivative times inner derivative. And this is basically this backward step, It takes the derivative of the output times the derivative of the next layer and so on until you reach the input layer. And then it takes the optimizer step. This actually updates the coefficients. And then you start again. Same x, but now different y dash, and hopefully less loss. And I do it 5,000 times, and hopefully this loss becomes very small in those 5,000 times. And you can see, this is actually quite a considerable number, right? 5,000. You can do it because nowadays we have fast computers. You can just let it run many, many times. So even if you have many small steps, it still adds up. Yeah, and then basically we are done and we have to test the model. So here I'm saving the coefficients. Here model state dict contains the coefficients of our neural network, which means in our case the coefficients of our filter. Right. So now I'm again computing the output. So this should know our correct detector. So I'm turning it back into NumPy. Here I'm adding noise, and I'm also computing it for the noisy data. So here I'm taking the model again. Right? So here's the model on the clean signal, here's the model on the noisy data, the noisy signal. So I have two outputs, and I can print the two outputs. So here in the plot functions, I print the clean output and the noisy output. And I plot the weights. And we will see that Pytorch in the convolutional layer uses correlation because it has the non-flipped signal. So, yeah, does the code make sense? So if you understand this code, you can now actually start building neural networks, convolutional neural networks. So this is actually quite powerful code because it contains all the ingredients you need to build a neural network. So let me execute it. So instead of gedit, I'm just using Python 3. See, it was quite quick, right? 5,000 iterations, and it's like in a second. So we are already done. So let's take a look at the loss function first. So here we have our 5,000 iterations, and I'm only printing every 100th iteration here, and so that you can see how the loss goes down. So the loss starts with number 3. So the scaling here is not quite clear, but we start with 3 as a mean squared error, and then it goes down here. 0.7, 0.5, 0.4, here 0.1, 0.08, 0.06. So you can see it's getting smaller and smaller, which means the output is getting better and better, or closer and closer to our desired output. So here it doesn't change much anymore, so here it's getting kind of stuck in this area. But still, we're getting down to 0.016. So compared to 3 at the beginning, right? So a lot lower. So here you can see the predictions, here are the weights, but those are best seen here in those plots. So here you can see the input signal, clean and noisy. So here's the clean input signal, blue, and orange here is the noisy signal with the added noise. Right. So slightly different from our closed form approach, but basically the same. So also it's kind of hard to see with your naked eye where the peak would be of this ramp, because the noise is relatively strong. So here actually this would be the highest peak. So if you just would use your eye, you would think this is actually where the signal is, right? Because this is the highest peak here. So here are now the Pytorch weights. Look at those weights. What do you think? They look kind of funny, right? Do they look like we expect? Well, we would expect, again, a ramp, right? Like in the matched filter case. Instead, we just see those up and down, and it's also very short, right? Kind of interesting, right? So indeed, it looks quite different from the matched filter, and this is because we specified not just the maximum output, but also a narrow output. So this makes the output also narrow, not just high, but also narrow. So you can see it here in the next plot. Here's now the output. So the blue is for the clean input, and you can see, indeed, we have just one peak here. Right? So this is exactly 1, as we specified, and also the neighboring samples are already 0. So this is indeed very narrow. And then we have a little bit deviation from the target. So here we have minus 0.1, here we have a small value. So these are artifacts, right? But they are kind of small. So if you just want to detect the signal, this is actually quite good. And then here the orange one shows the result for the noisy case. And indeed, for the noisy case, this is by far the largest peak. And also the neighboring values are much smaller. Right? We don't have this fat peak from the matched filter, but we really have a narrow peak where we can precisely determine the location of our signal. Right? So indeed, this was now successful. Right? So you would say that, I would say that this is more practical than the matched filter coming out of a neural network. And this also shows a little bit the power of neural networks. And of course, numerical optimization. So these are basically the pictures that I just showed you. You can see I have different noises. So in here I didn't have this strong neighboring peak as we just had. So this is the weights. The weights are pretty much the same. We found the same solution. And here the output for clean and noisy. So again, the noise is slightly different. But still a very narrow peak. Yeah, okay. I guess the time is up. Do you have any questions at this point? Neural networks are fascinating. Yeah. Okay, then this should be it. Thank you for your attention and have a nice day.